So we're going to do 3 examples for you today regarding heat, internal energy, and calorimetry. But before we jump into that, there's a couple little things I forgot to mention in the previous video, but good thing I made 2 of them. One is that we have 2 different values for the specific heats of different substances, and they just correspond to different units. Calories per gram Celsius or joules per kilogram Celsius. And depending on the situation, we might use one or the other. This is, sometimes we always use it with one unit or the other, but this time, depending on the situation, one will be more useful than the other. Basically, if we're comparing some type of energy like kinetic energy that becomes thermal energy, so we're going to set that equal to mc delta T. In that case, we have to use the value of C that includes joules, because this is going to be measured in joules over here. But then often we're going to have energy flowing from one object to another, so we'll have like M1 C1 delta T1 for one object equal to M2 C2 delta T2 for the other object. And in that case, as long as the units match, it doesn't matter what they are. And often we're going to be having heat transfers with water, and in that case it's kind of nice to use these units over here because C for water is just going to be 1, so then we'd pull out the C from this column for whatever the other material is as well. Alright, one other thing. I think I might have mentioned this earlier, but it's also important to remember that 1 milliliter of water has a mass of 1 gram, and so if you multiply both sides by 1,000, that means 1 liter of water has a mass of 1 kilogram. We're going to use that information quite frequently. Alright, let's jump into our first problem. We've got a stovetop burner that transfers heat to 1.5 liters of water at a rate of 400 watts, and we're going to assume that all 400 watts of this goes into the water. Maybe there's additional heat being transferred into the pot and into the air and things like that, but we're going to say that this is going directly into the water. If we leave the water on the stove for 5 minutes, what is going to be the change in temperature? So change in temperature, heat transfer, that should make us think Q equals mc delta T. But now we've got this watts thing going on here, and time, this is not time, capital T is temperature. So we've got another equation, power is energy over time, and the energy in this case is the heat, so we can say it's Q over time. So if we put that together, we get power equals mc delta T, capital T, over time. Be careful to not confuse your T's like I almost did. And so now we could just plug in numbers and solve for delta T. The power is given, it's 400 watts. The mass, if I have 1.5 liters, that corresponds to 1.5 kilograms. I might just write that in to remind myself that I'm using kilograms. Also, the power over here is going to be joules per second, right? So when I'm choosing my value for C, I can't use the value of 1 because then I would need calories and grams, but I've got joules and kilograms, so I've got to use this 4,186 for the specific heat of water. So 4,186. Delta T is what I'm trying to find, and then I divide that whole thing by the time. Now this is 5 minutes, but I've got seconds over there, and I need my units to work out, so I'm going to multiply by 60 so that I've got seconds on both of these. If we rearrange things a bit, we're going to get delta T equals 400 times 5 times 60 all over 1.5 times 4,186, and this will come out to be 19.1 degrees Celsius. Now, in PivNert, we always wanted to have temperatures in kelvins, but now that we're dealing with changes in temperatures, and the size of a degree Celsius is equal to a size of a degree Kelvin, or a Kelvin, I guess. So you could say 19.1 kelvins, or it's degrees Celsius. They're always going to be the same. All right. So there's our first example. Let's move on to the next one. If we've got a bullet traveling pretty quickly and it gets embedded in a block of wood, 40% of the thermal energy produced is absorbed by the bullet. What is the change in temperature? So we have quite a few things going on here, right? We have a traveling bullet, and what type of energy does that start with? Well, it starts with kinetic energy, right? And once it hits the wood, then we've got thermal energy. That thermal energy we're going to call Q because it becomes heat. It's this heat that was created by the collision. But we only have 40% of the thermal energy produced actually being absorbed by the bullet. So if we say that all of the kinetic energy becomes thermal, but only 40% of it goes to the bullet, we can say that 40% times 1/2 mv squared goes into changing the temperature of the bullet, so it goes to mc delta T. So this is our setup here. It turns out we didn't even need the mass of the bullet because the mass cancels out. So we're going to have 0.4 times 1/2. The velocity of the bullet is 230 squared. C, again, we need to be careful about which units to use. Since over here I was dealing with kinetic energy that was going to be in joules, I want to make sure and use the C that was corresponded to joules. And now I've got lead. If I jump back to my table here, this is on page, I don't remember, it's in your book if you ever need to look at it. Most of the time I'm going to write this in the problem for you anyway, so you don't have to go flipping into your book. Okay, so we're going to use 130 for our specific heat. Get my pen back here. So 130, and we want to find the change in temperature of the bullet. So we just divide both sides by 130. Plug this guy into our calculator, and we get a change in temperature of 81.4 degrees Celsius. So when you shoot bullets into things, they do heat up quite significantly. Alright, last one, and this one deals with what is called calorimetry. I didn't really talk about that much in the last video, but calorimetry is basically studying the heat flow from one object to another. You can have a calorimeter, which is a device to measure precisely the changes in temperature. You usually have some kind of water bath, and you put some object in it, and then you measure the change in temperature of the water. And from that, you can go back and calculate how much energy was in the object that you put in the water. Anyway, let's get to it. So we've got some iron that we heat up pretty hot, 400 degrees Celsius. It's going to be glowing nice and red. And then we put that in 1/2 liter of water, so not too much water. And it's at 20 degrees, which is about room temperature Celsius. So we're going to cool off this hot piece of iron, and we want to know what the final temperature of the system is. So there's a few things we need to think about here. They're going to have heat flow out of the hot object, so I'm going to have Q of the iron flow into the water. So since the iron is losing heat, I'm going to put a negative sign here, and the water is gaining heat, so I'm going to leave that positive. And conservation of energy tells us that what energy one of them loses, the other one has to gain. I also know at the end they're going to be at the same temperature. That is actually known as the 0th law of thermodynamics, because for a while it was just taken as a given, but then they decided maybe they should state it after they'd written the other 3 laws. They're like, okay, maybe we'll go back and add a law, and since it's pretty fundamental, we'll call it the 0th law. So given enough time, objects that are in thermal contact with each other will always end up at the same temperature. But it's not just going to be halfway in between, because it depends on how much of each object you have, the mass of each object. It also depends on the material, because the specific heat changes. So we have to plug in our specific heat equations for this. So we're going to have negative M of the iron times C of the iron times delta T of the iron equals the mass of the water. I'll just put H, specific heat of the water, times the change in temperature of the water. And I might as well write H2O on there. Okay. So we can go ahead and start plugging in some values here. Now here I've got specific heat of water, and I already mentioned what we're going to do with that. So I'll go ahead and put the mass of water, 500 milliliters. If this guy's in grams, I can convert this to grams. So a milliliter is 1 gram, so this is still going to be 500. C for water, as long as I use the same units for C over here, I can just use 1, which is nice. And I'm going to break out this delta T into a T final minus a T initial. The T final is what we're trying to find. That's the unknown. The initial temperature of the water is 20 degrees Celsius, and we can go ahead and use Celsius because we're using delta T's. Okay, over here I need the mass of iron. Don't forget the negative sign. That will screw up your answer if you forget that. So we've got 80. Now I need the specific heat of iron, and I want it in calories per gram degrees Celsius. So over here I look up iron. It's 0.11. 0.11, and the change in temperature of the iron is going to be the same final temperature. So I don't need to label these with different subscripts 1 and 2 or iron and water because they end up equal temperatures at the end. The initial temperature was different though. That was 400. Alright, so that's really all the physics. We are left with a fair amount of algebra here. So we're going to have to distribute this, right? So we're on this side we're going to have 500 times the final temperature minus 500 times 20, which is going to be 10,000. Over here we multiply 80 times 0.11 and we get negative 8.8 times TF, and then we've got that negative 8.8 times this negative 400. The negatives there's two negatives, so we'll have a positive, and that works out to be 3520. At this point we want to combine the terms with temperature in it and then combine the terms without temperature. So this guy's going to come over here and we're going to have 508.8 times the final temperature equals 13,520. Then we divide both sides by 508.8. So not all that fun, quite a bit of algebra, right? And it gets even worse if there's a third object we're considering. Like here we're ignoring the container that's holding the water, whether it's like a glass beaker or a metal container. If we had an additional container, we would just add one more thing that heat is flowing into plus Q of the container, whatever it happens to be made of. And that's going to give us another MC delta T. The final temperature will be the same, and it's more algebra fun, but eventually you get there. Let's get rid of this for now because we're not considering that. So we should probably finish off this calculation. Plug that guy into your calculator. You get a final temperature of 26.57, all around 26.6 degrees Celsius, which is pretty amazing because we've got a 80-gram piece of iron, which isn't that much smaller than 500 grams of water, and it's way hotter. But once again, because the specific heat of water is so big, it's able to absorb all that heat and not change the temperature very much. We only went up 6.6 degrees Celsius with a glowing hot piece of metal being put in a rather small amount of water. All right, enjoy your calculations. See you next time.